Hello there, PreCalc class. We're back with another Monday edition. 7.3 is up and ready. Multivariable linear systems here. So some of the stuff you've seen in Algebra 2, some processes and procedures are going to be a little bit different. So we're going to start off with a real easy one called using back substitution. So if we're given some system that looks like this, one has three equations, three variables, two variables, one, we can kind of go backwards and solve kind of easily. So this is our key piece at z equals 2. We can put that into the equation that was above it. So y plus 3 times 2 equals 5. Y here is going to be -1. Then we can take both of these, and I'll actually write out the whole line this time, and put both of these in. So we have plus 2 plus 6 equals 9, x equals 1. So our answer here would be 1, -1, 2. If you wanted to write it out like that, you can go through and check in all of them, but this does work. Something I want to mention before I move on to the next question is this form we have here that kind of goes down x, y, z, and kind of that slant is called, what is that, echelon form or reduced? I always get them flip-flopped. This is called row echelon form, which is really useful because once you have one of them solved for, you can kind of backtrack using this back substitution. Really nice and easy. So in our next question, it's not going to be nice and easy, and we're going to want to try to get it into row echelon form. And then specifically, the process we're going to use is called Gaussian elimination to solve a system. So we have this big old system here. And notice we have x's and y's, and then one of them is missing a z. These things will happen. What Gaussian elimination is first step is make one of the x variables have a constant coefficient. I guess I probably could have just said coefficient. The coefficient of 1, which we already have right here off the bat. That's good. Now 2, we're going to use that x to eliminate all other x's. So for instance, we have this first row here has an x with a coefficient of 1, and we can use that to add or subtract to the other rows to eliminate their x's. So to help us with some notation here, what we normally say is this is row 1, this is row 2, and that's row 3. So in my next line, I always want my row 1 here to stay the same. So I can write x minus 2y plus 3y equals 9. And then what I am going to do is I'm going to add row 1 plus row 2 to help us to know what we're actually doing here. So if we added these two rows, we're left with nothing here. We're left with a y here. We're left with 3z, and we're left with a 5 here. That's how we get that row, this new one, by combining row 1 and row 2. Now I also want to kind of adjust this too. So what I can say there is I want row 3 minus 2 of row 1. And maybe that's hard for you to hold in your head, which is fine. So off to the side, maybe you could write some side work. Say, okay, well, row 3 2x minus 5y plus 5z equals 17. And then we need 2 times row 1, so that's 2x minus 4y plus 6z equals 18. And then remember, we wanted to subtract these. So in subtracting these, we have a 0 here. We are left with negative 5. It's going to be a plus 4y, so that's a negative y. 5 minus 6. And I think we're here at this point. So let's write that over here. Okay, so notice we've eliminated all the x variables here. So those are steps 1 and 2. So step 3 is get a y not in the same row, where x has a coefficient of 1. And make that y coefficient 1. Luckily for us, that's already done here. So we have this y right here has a coefficient of 1. You may be saying, well, what about this one? That's negative 1. You may also be asking, what do you do if this was a 2? You would then just take this row and divide everything by 2. Okay, so now I kind of want to rethink of these as our new rows that we have all of a sudden. So let's say this is a row 1, a row 2, and a row 3. Row 1 just stays exactly the same. I'm not going to touch that. Row 2, I'm also going to keep the same because that's the y coefficient I'm using. Now what I am going to do here is I'm going to adjust the row 3. So what I'm doing here is I'm just adding row 2 plus row 3. We add these, we have a 0 here. We're left with what? 2z here. 4 here. Okay. And then our next step would be make the z term have a coefficient of 1. So how we do that is we can now rethink of these as row 1, row 2, and row 3. Row 1 and 2 are staying exactly the same. And to adjust this one, I'm just taking row 3 and I'm dividing it by 2. So we divide that by 2 and we're left with z equals 2. At this point, we can do like we did in the last question and use some back substitution. And if you're being savvy enough and have noticed, compared to the last question, this is exactly the same thing that we've gotten to. So we've now got it into row echelon form. Remember, that's where it goes x, then y, then z. It's just kind of going straight down in that diagonal. Once it's in row echelon form, we can use back substitution, and life works pretty easy here. So this is the Gaussian elimination method. You may be saying, oh, that's a lot of work. I'd rather just pick 2 and knock it down and make it 2 systems with 2 equations. As we continue to go on, and if you take future math courses, this is the method. It keeps everything in a nice, neat order. Okay. Now, sometimes we're going to get things that are inconsistent systems. And we did something like this last time, but we did it with just 2 equations and 2 variables. Let's take a peek at what it looks like with 3 equations and 3 variables. Okay. We're going to do that same kind of Gaussian moves here. Thinking row 1, row 2, row 3. Row 1, notice we already have x as a 1 variable, our coefficient. So that is perfect. Next thing we're going to want to do is make that a 0 and make this one a 0. So for the next line, we need row 2 minus 2 of row 1. Yet again, you can do this in your head. If you're not comfortable with that, writing it off to the side is fine. And we're subtracting 2 over row 1 from this, so that is 2x minus 6y plus 2z equals 2. When we're subtracting these, we're going to be left with nothing there. This is 5y, negative 4z, and a 0 here. So that is our new second row. And this one is just a straight subtraction since they both have 1 as their coefficient. Row 3 minus row 1. You can do row 1 minus row 3. It doesn't really matter either way. So if we do 3 minus 1, be careful of the negative. So that's like 2 minus negative 3, which is really 5y. Negative 3 minus z. And then we have negative 1 minus 1 here. And looking at these, maybe there's something that's kind of standing out to you right now. Specifically, we have a 5y minus 4z equals 0 and a 5y minus 4z equals negative 2. What we can do, kind of right off of this, which doesn't fit exactly the Gaussian method of dividing by 5 there, but taking a bigger look and noticing that those coefficients are exactly the same, we can subtract those. So here I would take row 2 and subtract row 3. 2 minus 3, that's 0. That's 0. So we have 0 equals 2. Which, if you remember from last time, this was one of those like contradictions. We can't have 0 equals 2. So this is where we have to denote that there is actually no solution. Because 0 does not equal 2, there's no solution, and it's just an inconsistent system is what we would call this. So remember that from last time. Whenever you have 0 equals some number that's not 0, that means we're not going to have any solutions here. So far we're seeing examples with one solution, no solutions, and you should be able to take a guess of what is coming up next. A system with infinitely many solutions. Okay. So this one's a little bit all over the place. We don't have the x here, we don't have the z there, but those are less variables to deal with right away. If we're using that Gaussian method, notice that spot 1, we already have a coefficient of 1. That's great. We can use that with row 3 to our advantage. So what I'm thinking is we rewrite the first 2 rows. And then this one we can get just by adding them together. Zero, 3y, negative 3z equals 0. Noticing anything here? Y minus z equals 0, and a 3y minus 3z equals 0. That is definitely something. Let's see what that's going to equate to. Here, our second move is we would want that y to have a coefficient of 1. We got that. We can use that to our advantage to eliminate the other y below it. So what we could be doing here is we want to rewrite the first two rows now. And then we can do, where are we at? Blue, row 3 minus 3 of row 2. And we're going to be left with 0 equals 0. And remember, when we get this from last week as well, this is going to mean that we're going to have infinite solutions. If you can get one of your lines to say 0 equals 0 by subtracting different rows. Okay, that is not quite enough though here. We want to know exactly what these answers look like. So let's say, since we know this is true, we know that y has to equal z. And let's just say, let's let y equal a, which means z equals a. Just some number. Some number a. From here, what we can do is we have that first equation. And let's put a into here. So a minus 3a. So x equals 2a minus 1. So our solutions all look the form x, y, z. We know all the x's are going to look like 2a minus 1, y is a, and z is a. So pick any number a that you want, any real number a, right? A is a real number, and this solution will work. And if you're looking for that fancier terminology, a is a real number. These are all going to be good solutions here. Okay, one final one to do here, and it's going to be a non-square system. So this happens when we have fewer equations than variables. Notice 2 equations, 3 unknowns. So this is going to play a little bit differently than 3 equations, 3 unknowns, like we've been having. Let's go by the same rules that we have been. We want that first coefficient of x to be 1. We got it. Let's get rid of the x's below it. So first line stays the same. Next one, I'm thinking row 2 minus 2 of row 1. Let's write that off to the side. And 2 of row 1, that gets us 2x, 4y, 2z, 4. We subtract these, we have a 0, positive 3y, and a negative 3z equals 1 minus 4 is getting us negative 3. Our next move is we would like this y to have a coefficient of 1. And see what we can do there. So I'll rewrite that first line the same. And then here, I want to take our row 2, and we can divide it by 3. So we're left with y minus z equals negative 1. Nothing really great here, because we don't have another line here where we can solve for z. But what we can do is we can take this line here and let's solve for y. Add that z over. We know that y equals z minus 1. And we can use this to plug it back into the first equation as well. So we had x minus 2y plus z equals 2. Let's see, x minus 2z plus 2 plus z equals 2. Combine like terms. We have 2's on each side. Is that still on camera? Nope, hasn't been for a while. Sorry about that. So we have x equals z, y equals z minus 1, and z is going to be equal to z, right? Because that's just itself. Z is equal to z. Kind of a no-duh statement. So what we can say here is we have x is equal to, what did we just say? Z, y is equal to z minus 1, and since z is z, we kind of have a nice outline of what our infinite amount of solutions would be here. But we don't want to write these as z, so let's make this a minus 1, and a. So our final solution set would look like this. Pick a to be any real number, and that's going to be our answer here. So you can just pick some random number if you wanted. Let's say, for instance, a is 2. So we'd have 2, 1, 2. And this should work for both of these original equations up here. And I'll just give it a whirl with the first one. So 2 minus 2 times 1 plus 2, does that equal 2? It does. 2 times 2 minus 1 minus 2, does that equal 1? Yeah, it does. So this would work for any number. It didn't have to be 2 there. You could have picked 100, 13, 17, 38. Pick your favorite number there, and it's going to work out just fine. Okay, I think this was the last one I had for us, yeah. So this is actually only half of 7.3. I got to come back later this week and give you the second half, which is a little bit different from this half. So the homework I had posted in class is still the same for this. I didn't see the second half to this section. So our homework is still 5 through 10, and then 13 through 37 odd. And I'll post the second half of 7.3 later in the week. If you have questions on this homework assignment, please leave a comment below, and I will make a response video. Okay, guys, have a great rest of your Monday here. Take it easy.